our friends on the way, so you can just get a 5 minutes head start. Okay, so it's a pleasure today to have Professor Miguel, who's visiting us from One Carmen, and finally we got to have a physical visitor coming, together with Professor Marcelo and a student from Modal, who's going to be talking on Saturday on networks and conflict. Today we're very much delighted to have Miguel give us this mini course, which covers the continuum aspect of complex system. So I'll just give you a brief introduction of who is Professor Miguel Mendez. So he's received his PhD in engineering science from the Deep Blue in 2018. He's currently assistant professor at the One Carmen Institute of Fluid Dynamics, where he teaches courses of modeling and control of fluid flows, measurement techniques, signal processing, and machine learning. He has extensively used data-driven methods for post-processing numerical and experimental data. This is what's going to be the topic of our lecture series. His main research activities include experimental fluid mechanics, particularly image-based velocimetry and image processing, reduced order modeling, flow control, and machine learning. So please help me welcome Professor Mendez, and we have 2 days with him, so we're lucky.
Thank you. Thank you very much. Thank you. Thank you very much for the warm welcome. I'm very happy to be here for this mini course. I guess you have received all the materials, all the slides and the Python codes that we will cover. You had a quick look, you have understood that it's going to be quite an intense course. So let's try to work together, let's say, make it as lively and interactive as possible. The title that we gave to the course is Data-Driven Model Decomposition in Fluid Dynamics, mainly because I am a fluid dynamicist, but and also because many of the decomposition that we will discuss come from fluid dynamics. But I hope you will quickly realize that this is, in fact, it's a set of tools that can be used much in many other contexts, far beyond the fluid mechanics. So among the various lectures that I prepared, the first one that I want to start with is trying to get some definition. So what is it, data-driven model analysis? What is that we call data-driven model analysis? And to address this question, I split it, let's say, following a historical perspective. So the first is the idea of looking for coherent patterns in fluid dynamics. Again, I'm strongly biased for fluid dynamics, but many of the tools can be applied in many other fields. Then we'll talk about some potential applications of data-driven model analysis in fluid mechanics. And once you have understood why these tools can be so useful and they are becoming so popular nowadays, we will go into the course overview. Okay. So before we go into coherent structure, I think maybe the best place to start is to look at some fluid flows. Okay, so this is a wonderful simulation which is not done by me. You will find this video on YouTube, and it's a flow of a narrow jet which is released on a cavity, which has a sort of a square-like shape. And this is a simulation which has several billions of degrees of freedom, takes several days to run. And what it simulates is what you can see, the jet entering into this big tank. And of course, the simulation is very short, precisely because it takes an enormous amount of time to run it for much longer. But if I ask you to look through all the complexity of what is happening there and all the narrow details that are happening there, I guess we can all try to picture this as some sort of a jet, which once it's released in this cavity, does not go straight, right? It kind of finds a sort of an inclined position. This inclined position is not stable. So what will then happen if the medium goes longer, you will see the jet going down and then up and then down and then up. It takes a lot of resources to simulate this. There's a lot of complexity going on, but for main application, being able to somehow draw a cartoon of this flow is enough. Maybe you're interested just in understanding what is the frequency of this oscillation, trying to understand, to get some information on the phase delay within these vortices and how the jet reacts, because maybe you want to use this for mixing purposes. Maybe you want to use this for measuring flow rates. In fact, it turns out that the way this oscillates follows a very precise law. It has a constant Stewart number, what we say in fluid dynamics, and you can relate the frequency of this oscillation to the amount of flow that is coming, and this can be used, for example, in microfluid devices to measure flow rates. But regardless of the application, the main point here is that we have a very complex problem, but somehow we can picture it. Our brain is very good at looking at these patterns and associate a cartoon to that. Here's another example. Here you have the link of the video. Is the flow past a block body, a cube in this case. And what you see is the famous carbon streets. So you have the flow is coming in this direction, and you have a separation of the flow from these edges. This separation is unstable and produces these large vortices. Again, you can draw a picture, a cartoon out of this, and somehow picture this as a very regular pattern which is happening in this low macroscopic pattern, let's say. And if you are, for instance, in fluid structure interaction, you're very much interested into that because these are vortices would excite some oscillation on the structure. So in that case, even if you have spent a huge amount of to simulate this down to its detail, then you usually go back and try to get the big picture. Now, don't get me wrong, I'm not saying that you don't need to simulate these details. The way this big picture moves depends a lot on the small picture. But here we try to focus on the big picture, okay, for some of the application that I mentioned. So to some extent, what we are trying to do, the way I like to picture model analysis, is some sort of cartooning a complex data set. And define some sort of way of measuring how complex that cartoon is. We use the idea of modes. Okay, we will say we have a lot of modes in this cartoon, few modes in this cartoon. I need much fewer numbers to draw this cartoon than to draw this one. This could be very interesting, for example, if you're doing image compression or in telecommunication. If I send you the information in a very compact way, I need to send you much less data. And if I tell you then how to decode the data, maybe I send you this and you recover that. Or maybe if you are in image recognition, for instance, and you want to distinguish whether you have a cat or a dog, you don't need this level of details to understand that you have a cat or a dog. Okay, so if you're or say for face recognition, if you find the pattern in the data, then you can quickly go towards the decision. I have more examples of fluid flows again because I'm strongly biased. This is the case of a plate that is moving and you have injected some smoke, and you see that again you have regular patterns coming there. You might have probably seen this one on the sky. So this is the well-known Kelvin stability. And when you have two streams of flow at different velocity, different densities, they can form incredibly regular pattern. Okay, so you can all draw a cartoon out of this picture. And the last two that I want to show you that are also found in the two, this one. This is the concurrent street passing airfoil. So it does not just happen on the cylinder. It's incredibly regular. It's impressive how regular. You could set your clock on these vortices. Or if you're cooking and you might have experienced the relay mass instability due to the fact that you have a bottom stream of flow which is warm and the upper part is cold, and you can trigger the formation of cells, of patterns that are very, very regular. So this is the lecture. Somehow it's coming from a very long debate, which I think up to today it's not entirely so on what are coherent structures. And here I'm listing some of my favorite references from the time where these ideas started to come. This one is particularly provocative and interesting: coherent structure, reality, and myth. So there was a lot of discussion on how can you objectively identify a structure and give a mathematical definition and say, okay, this one is a coherent structure according to this criteria. Okay, but there are many criteria. We'll see during the course many criteria to define what is a coherent structure. And I think that they mostly formalized with this tool that we see in this form, which is the proper decomposition in the 70s by John Donnelly. This booklet is very small, and we find it around 5%. And the main effort that this guy was having was to try, as I said, to define in an objective way these patterns, these coherent structures. And this triggered a lot of emphasis on dynamical system, on the dynamical system perspective of this coherent structure, because as we will see in the third lecture, you can use these coherent structures as a basis to project your problem into their mathematical form, and arrive at a dynamical system which is much smaller than the one from which you have started. Okay, so that started to bring the picture, the dynamical system picture, let's say, in fluid mechanics. Nowadays, this is becoming quite an established field in the sense that you have many more decomposition coming. Maybe 10, 20 years ago, you had the POD period, then now you have POD, DLD, many variants of this decomposition. So you have many different ways of defining this coherent structure, and we will see some of them here. I mentioned some references for you to go into more details if you want. Now, in practice, what we will be doing in this course is the following. We will take some data set, which, because of my bias, will almost always be a velocity field, but hopefully you have different data set that we can test during these days. And we will break it into modes. Okay, what is a mode? A mode for us would be some sort of rank 1 elementary contribution that is in this data. And again, because of my bias, I will picture this data as having some spatial coordinate and some time coordinate, but you might have other dependency there. And what we will do is something that you have been doing, I guess, in any course with PDEs, is splitting it with respect to some bases. Okay. And these modes, which I'm running here, you have three terms. An amplitude that tells us if the mode is important or not important. Have a spatial structure that tells you how this mode is distributed in space, and have a temporal structure that tells us how these modes are somehow important. Now, again, you see this when you try to solve PDEs with separation of variables. You look always for solution of this kind of expansion. But the big difference here will be that we will try to look for these bases directly from the data, okay? Without knowing anything about the operator or the PDE that has generated this data. We will see that to some extent, all of this can be written in the form of matrix factorization. And I believe that this kind of matrix factorization, you have already seen it. Can you tell me one example of this matrix factorization that you have seen? Yes, I think you're saying it, but I cannot hear. Anyone have seen a factorization of this form, where this is a diagonal matrix, this is an orthonormal matrix, and this is also an orthonormal matrix? SVD? Yes, SVD. So the SVD is one of the many ways in which you can write this. Okay, we'll see one specific example, but as I said, there are many ways. Now, again, why do you care about partitioning the data in this way? There can be many reasons. So the first, as I said, is the most probably the historical one, is to look for coherency. It can happen that few of these data, of these modes, describe a coherent pattern, like the one which we've seen before. So I think tomorrow I will give you this data set. This is a data set of an impinging jet. It's a jet flow which is impinging on a solid wall, and because of that is split into two streams. These are measurements. Okay, I don't know if you are familiar. These have been measured using particle image velocimetry. The idea is that you put smoke in the flow. You illuminate it with a laser, and you acquire a lot of images very quickly. And then you look for how the particle moves. Since you know what is the separation in your video, then you compute back the velocity field. Okay, so these are measurements with a very high resolution, both in space and in time. And it turns out that few modes capture the so-called Kelvin and Box hypotheses that are produced when the jet is released, and they can be used to describe their evolution. We can look for their typical size, their characteristic velocity, their frequency content. Maybe they are linked to some vibration or to some noise in particular. So you can get a lot by just throwing this, let's say, this data to this kind of decomposition. Or you might want to remove some of these modes. Some of these modes might be linked to features that are not interesting for you, maybe noise, for instance. In this case, you're using that as a filter or as a data compression tool. I believe many of you are familiar with the idea of filtering in the frequency domain, where you kill some Fourier modes. But now I will give you a set of tools where you can kill many other kinds of modes in the data based on other criteria, not just frequency, but maybe statistical correlation of the like. This was an example which we used again in PIV to clean images. So when you do the PIV, the measurement that I showed you before, what you want to have is like a sky in the night, like a lot of bright particles on a completely black background. Because if you have that, then it's easier to find the particles, let's say, and follow them. But in reality, you often have noise, light sources that are there, reflections. So one way to deal with that is to remove this by removing some modes. Okay, so you can use this to build a filter. You can use this to accelerate significantly all the linear operations. Okay, so here is an example where we were using a radial basis function regression to reconstruct a flow field, again from measurements. And what we obtain with this radial basis function regression is, again, a function of this kind where we have an analytic description of the field. So we can sample it everywhere. That's what is called super resolution. And when we solve this regression, we use a constraint optimization framework to put constraints, right? For instance, the flow is incompressible, so it needs to have divergence free. At the wall, the velocity should be 0, etc., etc. It is very expensive to do this for one data set. It takes of the order of seconds on that laptop. But if you have 20,000 images, that starts to be very, very expensive. Well, it turns out that all the operations that we're doing with this basis function regression are linear. So I don't have to apply it to all of the 20,000 snapshots, the 20,000 data. If I understand that this data can be reasonably well approximated by, say, 50 modes, then I will apply the regression to the 50 modes, and I reconstruct my high resolution from the regressed high resolution modes. You see, the gain in computational time was enormous. And the last, and you will have an exercise, I prepare an exercise for you by a taste of it, which is about reducing the computational cost of numerical methods. So I will give you a very simple PDE where we will have a velocity profile of a flow. Again, sorry, I'm very biased. If you give me an example in mechanics or biology, whatever, we'll be very happy to play with that. So the idea is that you have this oscillation, and I will ask you to solve this using finite elements or finite differences, and you will build a mesh of, say, 1024 points, and you will advance a dynamical system of dimension 1024. But if you look at the dominant POT modes, the dominant modes there, you have maybe 3, maybe 4. Okay, so what you can do then is to project this dynamic onto these 4 modes, and you solve for these 4 modes. So then you advance the dynamical system of dimension 4 and not 1000. Okay. So these are just some of my favorite applications, but maybe you will come up with other applications. Do you have questions on this so far? I hope they will come once you start playing with the code. So this is the overview that I had in mind. So I'm perfectly on time. I wanted to give you first just a brief flavor of what is data-driven model analysis, what we're going to do. And the other 30 minutes before we taking the break, I was thinking about a very brief recap of linear algebra. Now, everything that you've seen, everything, is purely based on very simple concepts from linear algebra, which you all know very well, I'm sure. I would like to refresh them just to make sure that we are all on the same page, that you're all familiar with that. And then we will have a small exercise session where I will ask you to solve a few problems just to get acquainted with that. Okay? So no questions so far? Take it as a no.
I had a question.
Yes.
So it wasn't clear the way you presented it. When you're considering thousands of snapshots, you're not after just getting the spatial decomposition of the patterns. You're after trying to capture their temporal evolution, of course, with a view to, in some sense, having a reasonable representation of the flow for predictive purposes. Is that what you have in mind as well? I mean, are we trying to render what we have in the snapshots, or are we trying to learn from these snapshots to be able to describe the dynamics irrespective of how many snapshots ultimately we have?
So in this course, we will not attempt the prediction part because it's only 6 out. But if it was 10, I would have, I think once you have achieved a fairly reduced compressed representation, then you have different paths towards trying to get the temporal structure.
So I just wanted to get clear because it didn't come across, I think, in the way you presented it. In the process of working through 20,000 or thousands of snapshots, the objective also is to build a description of the system that you are working with, which may stand on its own. I think that's important to emphasize, but it's not always the case.
It's not always the case. So for the moment, we will only go towards tools that will build this reduced representation, but we will not try to fit a model into this reduced representation. What we will try to do in the exercise of the Poisson flow, since we know the equation in that case, we will do what is called an intrusive ROM. So we will do a projection. I mean, we will manipulate the PDE to build this predictive step. But there are other paths as well. Another path could be to try to put a regressor, for instance, on the temporal the dynamics, like Gaussian processes or any kind of time series tool, for instance.
Okay.
Okay. More questions? So, as I said, all we will need are some basic notion of linear algebra, and I thought that it would be nice to recap them very briefly. First of all, we will be dealing only with discrete signals, but sometimes their connection to continuous signal will be important, and I will use this mostly as a warning. Then I think the main important message of this recap is the notion of linear transform, linear products on a orthogonal basis, because that is what we're going to use in the rest of the course. Then I will briefly give a very high level overview of the 3 scenarios that you can encounter for this framework, and then we go to the exercises. Now, the first thing that I would like you to keep in mind is that the way I would like you to look at signals, let's say, is as follows. So let's say you have a signal that for us is a vector that contains some numbers that you have sampled, for example, from your measurement or from your simulation. In the very moment you write that signal in that way, you are already implying the idea of a basis, of an underlying basis. Okay, so if I have, for example, that 3 there, it means that I have 3 times the basis that exists only there and nowhere else. Okay. And the basis that exists only in one point and nowhere else is just the Cartesian basis, if you want, in Euclidean space, or the delta function in continuous space. Now, because of that, so the delta function will be, let's say, the natural basis that you use every time you give a signal somehow. But the important idea is that each of these components that you're seeing here, so when you say, for example, this 3 or this 4, is just the result of a sort of comparison operator, which is the inner product. Okay. If I say that here I have a 3, for example, it means that here the signal looks a lot like 3 times this guy, let's say. Okay. So I would like you to look at this inner product as a sort of comparison operator. Okay. You all know what this means, right? Now, this comparison operator, we will use it also for 2 very basic notions. One is to measure the length of the signal, which for us is going to be linked to the energy that the signal contains, and to measure angles. So in statistics, you call this correlation. In algebra, you just call it the angle which exists between vectors. Okay. So when two vectors are 90 degrees, in statistics we would say they are uncorrelated. But for us, we would just say they are orthogonal. Okay, which is just a different way of looking at the same thing. So just build this connection, and now imagine that your signal gets very packed, very dense. You have many points, so that it becomes continuous. Then, of course, the summation in this product will tend towards an integral. Now here, these are not entirely the same units, right? And this is delta t here. So I want to draw this connection because I will show you an example of two bases which are orthogonal, for instance, in a continuous sense, might not be necessarily orthogonal in the discrete sense unless you do some stuff. So this is the continuous version of this, which is just an inner product, and again is our comparison operator. We have also the continuous brother of the deltas, but here we need to do some technicism which I want to skip, which is into the fact that if you want the area under this delta to be unitary and this delta is getting infinitesimally small, then it has to go towards infinity. But we will not use this property in the remaining of the course. What we will use, and I would like you to see this in every possible way, is the idea of writing a signal, any signal, with respect to a base. So for us, a signal, whether a snapshot or a time series, is going to be a vector, as I said. We usually represent this vector with respect to a basis. The default one, if I tell you nothing, is going to be the Dirac basis. That's just a Cartesian basis. And here I'm writing it either in terms of vector or in terms of sequences. So a time series is a linear combination of time series here, and a vector is a linear combination of vectors here. And the way you can write that, and the way we will write this in the remaining of the course, is in the form of a matrix multiplication. Okay. So that set of sum of products, a linear combination of these products, can be written as just a matrix vector product, where in the matrix you store all the elements of your basis, right? Here you put all the coefficients with respect to that basis, and here you get your result. Now, it can happen that I give you a basis, that will be the exercise. I give you a basis, I give you the signal, and you have to look for the coefficients. Okay, in this case, you have to solve a linear system, right? And we will generally say that when you solve this linear system to look for these coefficients, this coefficient is the representation of that vector with respect to the spaces. We're doing a transform. And when we use these coefficients backward with the basis, we're doing an inverse transform. This is going to hold if you are using Fourier transform, if you're using Wavelet transform, Chebyshev transform, any linear transform will be essentially based on this idea. Okay. Very special case, of course, is the case where your basis is orthonormal. So in this case, it just means that taking the inner product between two guys gives me either 1 or 0, depending on whether I'm taking the inner product with respect to that specific element, which also means that let's say B dot, here the dot denotes transposition and conjugate, B dot B gives the identity. So, and that is the orthogonality we use then later in the exercise. If I give you a vector, U, and I say that this vector can be written as a linear combination of these coefficients, and then I multiply, I project on say B1, what is going to happen is that you will have all products of B1, B0, B1, B1, and so on and so forth. But because of the orthogonality, what is going to happen is that they will all cancel except the very specific one, right? And because of the orthonormality, in that case, we will get precisely that condition. So in this specific case, transforming and anti-transforming will become extremely simple. Can you give me one popular example of a transform that that respects this condition?
An example of quantum mechanics find the probability of one state multiplying the state by the derivative, applying the derivative v1 and we can find
the coefficient. I'm not in quantum mechanics, so I was thinking about something much easier, just Fourier transform. That was what I was having in mind. Okay, so the Fourier transform is one case where you will actually compute it in this way. So in the case of the Fourier transform, taking the inverse because of this property is incredibly easy. Okay, and in the case of the Fourier transform, the matrix B is also such a special properties that the product can be computed in a very efficient way, and you go towards the FFT. How many of you have used the FFT already? Okay. So the FFT is nothing more than a way to compute the multiplication in a fast way, because the matrix B, in the case of the FFT, has a lot of beautiful properties, which we will see also in a few minutes. But another example could be wavelets. I don't know if you have used the wavelet decompositions that also fall in this category. Now, warning, here what I want to say is that in general, this go back and forth might not be lossless. Okay, you might lose some information in going back and forth. Okay, because if this is your inverse transform, and I plug here UB, which is coming from the direct transform, what you will have is U equals B times B DAG times U again. And there's no guarantee that B DAG is the identity. Okay, we'll play with this stuff. So is this clear, right? Quite obvious things. Now, there are three scenarios that we will meet more or less. So again, transforming U, linearly transforming U with respect to a certain basis means solving a linear system. NU is the size of our signal, and NV is the number of bases which we are putting in. And now you can find three possible scenarios. You have no solution, and that is typically the world of reduced order modeling. You have just one precise and exact solution, and that is usually the world of filtering and signal processing. Or you have infinite solutions. That is the world of analysis. Now, no solution is because your system is what we say skinny. So you have too many equations, and you have fewer unknowns. Okay, so in this case, unless you're very lucky that your vector lies exactly in the span of the columns of B, you will not be able to find an exact solution of this process. And this is precisely what we will be interested in a few moments. As I said before, I was compressing from 1000 to 4. We are in this world. There's no hope, no guarantee that we can come back. In fact, there's no hope that we can come back. But we might not care. We might be, let's say, it might be good enough for our purposes. The case you find in signal processing, often, in the case of the FFT, for instance, is the case in which you have a number of bases equal to the length of the vector. So this is the matrix square as an inverse, so you can go back and forth without any problem. You can type FFT and EFFT, and you go back exactly where you start. Okay, it's a lossy transform. Or you can have a fact case. So in this case, you have too many solutions. An example of that is a continuous Wavelet transform, where you have many bases, which are all just replica of the same that has been shifted, and you use it for analysis purposes. In that case, you're not really interested in being able to reconstruct your signal, but you're interested in looking for patterns in that signal. So you, let's say, compare it with many bases. Okay. So graphically, the world we will be playing with is the first world of the world of the least square solution. As I said, I will generally not have an exact solution. So you will look for the best solution. What is the best solution? you project on the basis. Okay, you try to minimize the error that you have when you take this approximation. The operation of projecting, as we saw, is multiplication by VDAG. Okay, and this gives you that equation. So if you have, say, in general, if you have this situation, and you multiply everything on the left by VDAG, if your basis was orthonormal, you were done because this was dead. But if your basis is not orthonormal, you are not done. You have to solve now this system. It is that if you have projected your data set into the span of the basis vector, and then you have to solve this system. Okay, so in this case, you will have a situation of this form. Okay. And the inverse transform will be, well, do you remember that the inverse transform is this? So if I now chain this into that, you obtain B times all of this. And now I'm not entitled to write this with an equal because there's no guarantee, it's usually not going to happen, that I go back to the same point. Okay, but this is, I would say, the essence of the course now, because let's assume that this is a vector of dimension of 1000, and I'm using 100 bases. Then this is a vector of dimension of 1000. This is 100 numbers, and so this is a matrix of size 1000 times 100. So the representation of this 1000 vectors with respect to this basis contains 100 numbers. So if you are in telecommunication, I can decide that I'm going to send you, then I need to send you 1000 numbers. Or I send you only these ones, but then I have to tell you what was the base, right? So that then you can recode it back on your hand. You see? Or you might decide that once you've projected into these bases, then you might want to remove some elements, because maybe you're doing filtering, and so when you come back, you're going to have a lossy decomposition. Okay? So this one is the operator that I was calling the P, okay, which is, what is the dimension of this? What size is this? In this specific case? 100. No, this would be 1000, 1000, right? So this is 1001. So let's say if I only look at this one, right? This is 100. This is 1000. So this all stuff is 100 times 1000. Now in machine learning, you will call this the encoder. Okay, so it's encoding our information into a smaller version. There are many clever ways of doing that, such that you don't have this. And the least you will ask is that your method, sorry, this goes like that. Right? The least you will ask is that this matrix is orthonormal. Okay, so this will be our encoder, and this will be our decoder. Okay, and the whole process of chaining the two is called autoencoder. Okay, is this clear? Now, all the decomposition that we will see, POD, DFT, Wavelet, MPOD, DMD, everything can be put into this picture. Okay, so if you have understood well this picture, the rest will be an easy work in the file. And when you put this into dynamics, you have to imagine that this vector is evolving in its own space according to a dynamical system. And this guy is some sort of a shadow of this guy. Okay, so you might try to see how the shadow of your thing evolves. Okay, is this clear? So reducer modeling is the world of the shadows, where you look at how the shadow of your giant vector is actually moving. Signal processing is the world of people that wants to go back and forth without any problem. The FFT is one example. You might want to go on one side, maybe remove some Fourier modes and come back, okay, and for filtering. So the necessary condition here is that you really want to be able to go back and forth easily. And this is the case where the shadow is on the other side, in the sense that your original data is the shadow, and the vector that you want to build to approximate is just too large. So you have many possible ways of doing that. So in this case, which one do you pick? There are many criteria. The usual criteria is to pick the one that has the least energy, the least length. Okay, but the problem in this case is really badly posed to be able to come back. Okay, this is the world of continuous wavelet transform. And we will not be in that world. We will mostly be in this world, and occasionally I will be in this world. Okay. Is all of that trivial? Everything feels confident with that? Yes. Good. So, yes.
Is there something common between wavelet and
Yes. So wavelets offers you one possible beam. And there are different ways of building the wavelets. So one way is what we usually call the DWT, which is the dyadic wavelet, where you will build your bases using the usual tricks that you have in the continuous one, so shrink and shift. But you do that in such a way that you make sure that the resulting basis B is square. And so you want to stay in this world. Okay. The way you do that is by doing, I don't know if you're familiar, like a dyadic. So you don't take all possible shifts. You take only very precise shifts to make sure that you are in a situation where the number of wavelets that you've picked is the same as the number of points in your vector. And so you can go back and forth as you want. The other approach is continuous wavelet transform. In this case, if you have your signal, you will compare it with many possible wavelets. Maybe, I don't know, you have a wavelet like that, then the same wavelet shifted a little bit, then the same wavelet shifted again a little bit, and you have, say, 100 possible shifts of these small wavelets. Then you stretch it, and you do this again. Then you stretch it again, and you do this again. So what is the basis in this case? You will have 100 times all the time for all the stretches and all the shifts. So for all the shifts, you can build a set of bases, and stretching, you have another set of bases. So in this case, NB will largely be go above NU. So that's also why it's not so easy for a continuous wavelet transform to come back. But you usually are not interested in that process. You use the continuous wavelet transform to have information about the time and frequencies, right? Because you compare each of these. You want to know how much these. Let's say that I have a wavelet basis like that. For large guys and large guys. And here I put very large guys. The fact that my signal in this area looks a lot like this and not at all like this means that in this area I have higher frequencies and not lower frequencies. You see? That is a process of analysis. You're just interested in analyzing what frequency do I have in this portion of the domain. Okay. Whereas here, you're more interested in the possibility of coming back. Okay.
So when we use the one solution, yes, the clear transport.
Yes.
We transform on function and filter the transport and transform the line.
Yes.
In the case of the produced order model itself, this filtering is happening depending on choose basis.
Yes.
When we transform it, there is some filtering, you know, we're getting some.
Exactly. So in other words, here you have filtered because you have decided to kill some UBs. Here, even if you keep them all, you are already filtering. You see the difference? Here. Here, when you filter, you go into UB, then you multiply this by something, as usually a transfer function, and then when you come back, some of the UB have been removed, so you have used. Everything clear? So I will give you the exercise. I mean, you look at what kind of exercise I have in mind. It's very simple, just to get your hands onto the Python, and then we have a little break. Okay. So the exercise is very simple. So here I was just making a connection with the continuous word, but we will see it. I prefer looking at that directly from the exercises. So these exercises are in the Python exercise session 1 to give. And normally if you run this code, it will not work because it's full of holes and you have to fill this code. Okay. There will be 4 questions, which are the following one. I would like you to use this. Okay. So the questions are the following. First, I give you a data set, very simple data set, which contains 300 points, and which is nothing more than a uniform sampling of a function, sinus of sinus of x in the interval minus pi pi. So if you plot that function, it will look like a sinus, of course, right? Something like that, let's say. Right. Then I ask you to compute the encoding with respect to this basis. The basis will be 1, x, x squared, x cubed. So yes, I'm asking you to do a polynomial fit, but don't use polyfit. You use this. Okay. Then that is exercise 1. Exercise 2, I will ask you to repeat the same exercise, but now instead of using these bases, you use another set of bases. You find the equation in DC, which are the Legendre polynomial, which are designed to be orthogonal. Okay. So the least you will hope is that this is identity. But this is true in a continuous world. And I would like you to check if it's true also in our discrete world. Third, I will then ask you to compare what you obtain, what you have written from your Legendre basis with what you obtain by using a QR factorization of this matrix here. Okay, do you know what is the QR factorization? No? It's a factorization that is designed to orthonormalize the column of a matrix. So if the matrix B has columns that are not orthonormal, the output of this factorization will have columns that are orthonormal. It's like taking your vector that were like that, then QR comes and stretch them such that make sure that they are orthonormal. Okay. In the last exercise, I will allow you to compute the FFT, but using this, so don't use FFT. Okay. Then you compare with FFT, and we see that you obtain the same result. Okay. So everybody take a little break. You think it over, and then, or you want to start now. It depends on your full of energy. You want to have a little break. Well, you can choose. I will have a little break. Okay. Say like 10 minutes.
Yeah, I think it's great now. You can run for coffee and cookies and stuff, and then we come back and
then you go.
Yeah.
Okay.
Okay.
But if these exercises are simple for you, the rest of the course will be very. Okay.
I guess you can guide it. You can team up.
Yeah. Let's team up.
Let things get done faster.
Yes.
What about you guys? Did you mix the Lebanese university and we blocks with there you go.
Yeah, we have like a team here.
Yeah. So there you go. You have one team here and a team here. So 2 teams, and I think
Okay.
process. Fast.
I think one good way of tracking this problem, but any problem part, is to first make a list of things. What would you do? Okay, what are the things that you're going to do? And then the rest is mechanics. Okay? Then when you are experienced, you go to them. Do it yourself. So what would be the first step for you? So we are here, right? So I want to fit a basis which has 1x, x squared, x cubed. Hmm? Yes, we have up to x cubed. I will write here all the things, and then there we write the procedure. Okay. So in this case, our signal is that dynamics of thing, and we want to write this as a linear combination of bases. We were going to have only 4 of them. So if I use the same notation, say I have R0 and D3. If you're Python, if you're MATLAB, you go from 1 to 4. But there's no MATLAB user here, right? It's fast. Yeah. Good. So, and here our basis vectors are 1, x, x squared, x cubed. And so you have to find 4 numbers to give me 4 numbers. So I'm open to suggestions. Before looking at the goal and before starting thinking how what actually to do, tell me what should be the procedure.
Find the coefficients.
Yeah, that is the end goal. But before we say again? I cannot hear you, sorry. Sampling. Okay. So to construct U. Yeah, good. So first construct U. And that is going to be what? Another thing, every time you write a step, write what will be the output of that step. Okay? So the output of this procedure is going to be what? A vector, a matrix, a tensor.
1 for x and 1 for the sin x.
We will obtain 2 vectors. Yeah, so good. So we will need x, which is going to be a vector, which is sampling from -pi to pi uniformly, and it will have 300 points, we said. And then we will have u being sinus of that thing. And this is also a vector of like 300. Everybody agree? Good. Then I want to hear someone here. Next step, what will be? Yes. So we need to we need to write the equation. So write the equation. What would be the equation in this case? We need to solve a linear system, right? What would be, how would we write this equation?
You should be equal to one basis
Excellent, excellent. Tell me about the sizes. So this is size.
Yeah.
Yes. This is size. Very good, very good. And so this is obviously. Is there any hope we can get an exact solution here?
We're moving from the first one is very big. 300 is much larger than 4.
So we are in the first case, right? Was this linear? So there's no way we will have an exact solution, right? So we can only approximate that. Good. I'm not going to ask you yet how to get the B. This is a detail. I want to get until the end. Once you have this in your mind, now the purpose is to find this UB, which I will write it here to make it very clear, is going to contain 4 coefficients, say C0, C1, C2, C3, which are the 4 coefficients associated to each of those bases, right? Good. Next, in this side. What's going to happen next? The inverse. This is rectangular. There's no Strictly speaking, no inverse.
To multiply by transpose.
Yes, very good. So this operation is the projection. So we will have B dot U is equal to B dot V times UV. And now here. Do we have any hope this thing will be identity?
Yeah.
We don't do if you reply I don't know, it's a very good reply. We don't know. Good. I like it. So now what is the dimension of this? 4 by 4. 4 by 4. This is 4, and this whole stuff now is 4. Oh, this is a system. This we can solve. This we can solve. Okay. So if you want, you could call this, I don't know, y equal a times x. I don't know what is your favorite way of maybe b, ax equal b. And now you have to look for this x, okay? So there are many good ways of solving a system. I will now pick the worst. And I will say ub is equal to, I will invert this. Okay, the problem is small enough that we can afford doing this. Everybody agrees with that? Good. Now, before we go there, the last point, would you like to take, before actually doing, so that's the normal first workflow, then before you actually start doing, you should think about what to expect. If there is any insight about the problem that you could somehow feel, this is the good moment in which you should try to put it, okay? Because then you can check if your results are good or bad and debug and all things, okay? Do you feel like taking a guess on what could happen to the 4 coefficients? So remember that our sign, our function is something like that, if I'm not mistaken, right? Will you take any guess on this coefficient? For example, what could you tell me about the coefficient C? Good, good, good. I like it. That thing is odd. So I will not expect x squared to say anything, right? And also I will not expect this 1 to say much. Okay. Go ahead. Tell me what is C0, C1, C2, C3. We will expect them at the end to be 0.
They're very close.
Yeah, very close. And what do you mean by very close?
10 to the minus 16.
Still done. Very good. Very good. We have good. Want to share how you did it?
So in this case, 5 is.
But you first build the B.
Yeah.
Yeah. So okay, you've done it all of it. So first you build the B by creating a matrix and then putting into the columns.
Then there's 1.
Right. Okay. Nice. 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 It's not entirely a random matrix, but we will come back to that. I'm glad to hear this word. This will be our B. You agree? Good. And then the rest is just solve or inverse or whatever. I would like to have at least one from this team with the solution, and then we go.
First, I know that x is 0.
So let me check myself. So we were here.
Yes.
So here I was building the matrix, and then I compute this. So I have, if these results.
I had it for for x squared, the coefficient that's not plus x squared 0.
Exactly 0.
Yeah. The first one is 4 times 17, and the others are similar.
So you use probably a better approach to me. Look what it is. Can you all see what it is? NP ln algebra inverse of P transpose of P times P transpose U. Okay.
Maybe I did it directly. Yeah, I just called any square estimation number. So that's
no. That is a better one. Don't use now only NumPy here allowed. Okay.
But aren't they doing the same stuff?
Yes, but in a much better way. You don't do this. Yes. Plus, this system has very special properties. This matrix is symmetric. Who is in computing? What would be your guess? What will be the method of choice if I will ask you to compute this? Yes. That would be much better. Okay. So you guys have this? Okay. Here, there, but no. Okay. You can only use NumPy.
Now we want to non-equations for the drum.
So you will change the basis, okay? In fact, everything will be the same. It's just that this will be a different one, right? I think the question was if you should check if it is orthonormal. Okay. The Legendre polynomials are designed in such a way. You have to be careful here that the Legendre polynomial should respect this condition. So you should first think about the domain. Minus pi to pi. So first you have to do a scaling. Then you build your Legendre polynomials. You will build your B, okay, with also 4 terms. And then I'm asking you to check what happens here. Is this identical? By the way, if those that have solved that, have you tried then to make the prediction and to compare? How does it look if you compare that? Yes. Very similar, right? You're one step ahead. The blue one, I don't want you to put the blue one here. Yeah, sorry, I should have even used less. Yes, it's very simple. It's very simple. We'll come back to the blue one very soon. But first, so the next step that I would like you to check is now to change B. Okay, instead of using this B, which is a very bad B, I would like you to build the B in a different way using the Legendre polynomials. And there is the link on Wikipedia where you go on the table and you find, maybe I will do it for you, and you find their expression. Now, these polynomials are designed to be orthonormal in the continuous world within the domain -1, 1. So be very careful because we are not there. We are in -pi pi. Okay. And they are defined in such a way that the continuous inner product is, I mean, with respect to this continuous inner product, they are orthonormal. And I would like you to check if they are also orthonormal with respect to our inner product, which is just the plain vanilla inner product. If you're looking for them, this is the expression of the polynomials. Okay. And then right. Sorry. They said they're already there because I didn't believe, but okay. There was first the comparison with the blue curve. Now we have another grade, and then one. So I will try to let them visit the conditions, and after the break, yes. So after the break is going to be here. So we must finish the whole exercise before the break. We should help each other into. I will repeat the question. So I would like you to check that the basis of Legendre polynomial, carefully sampled because the domain has to be changed, which is supposed to be orthonormal with respect to the continuous inner product. Is it also orthonormal with respect to our inner product, which is just the simple B transpose B? Okay. The first that has the raise the hand so that So I will show you the solution just in the interest of time. Of course, then I give you also all the code with the solution just for you to play, but first you have to try, okay? So here I was doing this. Look, so this is our domain. I restarted from scratch, okay? From minus pi to pi, 300 points, this is in space. And then here I do x divided by pi. Why is that? Because I want my domain to be between -1 and 1. Otherwise, there's really no hope at all, okay? Then I define my 3 basis vectors. So the first is a vector of 1s, then I have x, then I have 0, 5, 3x squared minus 1, and blah, blah, copied from the table, okay? Then I stack all of them into a matrix. Now, this can be done in 100 different ways. The one I picked, you can see that in Python, different than MATLAB, a vector can be really a vector or can just be a list of numbers, having no other dimensions, okay? So here I define them as the dimensionless in the other dimension. So to stack them, I use this stack, okay? And then I have to transpose because otherwise we start to put them not in the right order. What I'm doing is an extra step, not necessarily needed, but I am also dividing by the norm of each of them to make sure that they will have unitary length, okay? But still, now, if I take this check, this should hopefully be identical, okay? Do you have that? I think it's already provided.
I have a question.
Yes.
Isn't there a way to sequence potential data?
Yes.
Instead of like
absolutely yes. The Legendre polynomial could be generated in a much better way than that.
So I was thinking for a way just to produce them without typing that.
Absolutely, yes. So indeed it will be, but it's a bit out of the scope of this exercise. But yes, it's when you could use a recursive way to generate all of that.
Okay.
So have you opened this check? If I open this check, what I obtain is I open this check, I obtain this. Are you happy or not about what you see? Are you? No, this guy is really annoying here. Okay. This one is really annoying. Now, the funny thing is, so who's this guy? This is the projection of the basis number 1 on the basis number 3. Okay. And it was supposed to be 0, but it's not. It's not so close to 0, in fact, okay? Are you shocked? So this is a warning to tell you that this inner product and these inner products are not exactly the same. Now, you could, to make the fair comparison, you should multiply this by delta x, right? So that this is a summation of all the entries. So what is this? This will be the summation of all, say, basis n evaluated at all the x, so I say all the entries, times the basis m evaluated all entries times delta x. This will be a very rude approximation of this. You agree? Very rude, in fact, but why not? Now, the least that you should check at this stage is what happened to this specific guy as I increase nx. If you increase nx, so the number of points that you're putting into your domain, this delta x will decrease, okay? And what you hope is that this number, as I increase n, does not grow more than what the delta x decreases. Because if this is the case, then there's no way we can have the orthogonality. We live in two completely different worlds. Now, if you play with that, you will see that that does not happen. You will see that this number tends to be more or less the same, whereas the delta x is decreasing. So at the limit for the delta x going to 0, we're having many points, we will approximate this well. Or there will be a much better way of handling that. What would be a better way of handling that? If our goal is to approximate this integral, there are better ways of computing an integral numerically than just doing that. Yes. So the line that follows is a check where I'm using the trapezoidal rule. And you will see that this one is almost 0. Okay. Already with 300 points. So the bottom message is, I am for this course using a very rudimental approximation of the true inner products. Okay, very rudimental, but good enough for what we want to do. Okay, is everything clear? Then I was asking to do another check, and some of you when plotted the results saw the blue curve. What was the blue curve? Taylor. And what would be the Taylor expansion for the sinus?
X minus.
Say again? Yes, x minus
X
minus 1, so minus 1/6. So Taylor will give you 0 here, 1, 0, minus 1/6, no? Okay. Whereas you got something completely different. Are you shocked? Not. Taylor is really good, huh? But it's not this small. Good. So Taylor is designed to approximate your function locally, very close to the point where you are expanding this stuff. Whereas these tools are designed to approximate your function globally, so within the whole range. Okay. So don't mix the things up. Okay. They are both two series expansions, but with completely different purposes. Okay. The last exercise, I think, is the, no, first I have them, but this one is solved. So let's walk together through it. This part is okay? You did the check?
Just for the QR decomposition. Okay, I understood that we want to contract the contraction. The representation of Muslim, but what's the mapping condition?
The QR is not linked to the compression.
Yeah, I didn't understand quite mathematically.
Got what is the QR doing?
Yeah.
But the QR is doing basically, if you have vectors which are like that, you just push this one here like this. Okay. The QR is using, usually you can do this with different algorithms. With a popular one is Gram-Schmidt orthogonalization, or you have Hausdorff reflection. But the whole idea is, you gave me a basis that was like that. I don't like it. I will push this like that. Okay. All it's doing is reorthogonalizing your original basis. Okay. So if phi is a matrix of dimension, in this case, it is going to be 300 times 4. So I call it phi. So here we're doing that. This is 300 times 4. This will be 300 times 4. This will be 4 by 4. So what the QR is doing is taking the columns of this matrix and trying to make them orthogonal. Okay, using Gram-Schmidt. Usually you don't do the QR with Gram-Schmidt. It's numerically unstable. You do it with Hausdorff reflection. Yes, but the philosophy is, at the end, is the same. You're trying to put them straight. So the outcome of Q should be an orthogonalized version of this. Okay. And I ask you to compare that with the Legendre. And that were the plots which I'm doing here below. Okay. Are you there? Are you in this one? If you compare them, what you will see is that they look quite similar. So they can be defined up to a minus, okay? This matrix, let's put it like that, just tells you how much the Gram-Schmidt or Hausdorff reflection had to work to make it to make it, if this was already orthonormal, this would be identical, okay? So the first one, for example, I get it with a minus difference. They are all defined up to a minus, okay? This was my second, and here I have my third. So it's pretty close. You see, this is, for example, the third polynomial. Pretty close, but if you zoom, in fact, you can obtain the Legendre polynomial starting from this one and doing Gram-Schmidt with this inner product. You will fall back to the expression, analytic expression which you have seen, okay? This is doing a bit numerically. The inner product is not exactly the same. So those guys will not be exactly the same, but they will be very close. Okay, if I zoom here. My computer, I think I also need to change my computer. Okay, everything is clear, ready for the last? The last is the most difficult. So the last, I'm asking you to do the same, but now with the Fourier decomposition. So now you have to build your basis B from the Fourier basis. And I will ask your help. Let's try to do this together. What is the Fourier basis? First of all, we are in the discrete world. So even if we call this a transform, this will not really be a transform. Okay, it's to be more a Fourier series because you're going to have a finite number of frequencies. If I ask you to sketch a bit roughly what is the Fourier basis without going into the details, but really roughly, then we go to the details together. What will you tell me? So the general base is n, okay, which in this case we are making it as a function of space. So let me put, well, I put m and I put g. No, g because I put I because I use g. J for me is this. Electrical engineers? No engineers? Physicists? Yes. So for you it's I, right? Put I, then don't put this, put another thing, I. Okay? Can you help me? Sorry? Yes, I would like to know what should be the Fourier basis. Before we had B0, B1, B2 being our basis. Remember we had 1, x squared, x cubed, or we had the Legendre. And now I want this to be Fourier, the Fourier basis. Yes. If you do cosine, it would be a cosine transform. If you do sine, it will be a sine transform. Yes. Yes, which normally what would be the fastest way of writing it? Yes. It would be an exponential. Yes. Not minus. Not minus. We come back to that famous minus. Not minus. The minus is coming from somewhere else, okay?
And that's
X pi over. Now you are going already one step farther. I want to derive it with you. So it's going to be X, and then I will put a general wave number, okay? Now the wave numbers will go with n. So if you take the basis number 10, you will pick the 10th wave number. Okay. And if you want to evaluate that basis at position number 20, then you would put the 20th here. Okay. Agree? Now, in the easy and the more straightforward implementation, we will assume that both x and k have been equally sampled. Okay, so my xr is going to be r times a certain delta x. And for the same reason, kn will be n times a delta k. Okay, I'm sampling uniformly both the wave numbers and x. Remember what I showed you today before? I said I want my matrix to be square because I want my life to be easier. Which means that if I have nx points here, how many k's? Also nx. Let's call it capital N if you don't want to be confused. Capital N is both nx and nk if you want. It's the number of both positions and frequencies. Okay. There's not much to say about delta x, but we can say something about delta k. Normally, I give a lecture of 2 hours on this delta k at VGR, okay? Because that make a lot of differences in signal processing and how you define this delta k. I will pick the simplest possible explanation and define this delta k as, let's say, the smallest wave number that you can have in your data. Why is that? Because when n is equal to 1, then kn will be equal to exactly delta k. Okay, is the smallest wave number that you can see in the data. This has a lot to do with Nyquist and a lot of things which I'm going to completely skip here. Okay, so what is the definition of wave number? A wave number is 2 pi over a lambda. Okay, so the smallest wave number which I will have in my set is linked to the largest lambda that I have in my set. You agree? If my signal has been sampled from 0 to L, what is the largest wave number that you can actually think of when you build this comparison operator, which we saw today? 2L will be ambitious. To be sure that I actually have one period, I should see at least one period. So I will say L. But what you said could be a very good idea in many problems. Okay, the standard definition that you have in FFT is saying if I want to say that I want to compare my data with one period, I need to see at least one period. Okay, but what you said is not completely wrong. Okay, there are transforms that use that. Okay, so if this is the case, then the largest lambda is also the whole length of my thing, which is also equal to n times delta x, right? Is the largest x that I have. You agree? So what is now Bn of xr? It will be e to the j. That is going to be r times delta x, and kn is going to be n delta k. But delta k is 2 pi over capital N times delta x. Agree? Do your simplification, get rid of this delta x. And what we see here is e to the j. Then we have, let me write it like that, 2 pi over n times r times n. You agree? Isn't this beautiful? What you have now is really a beautiful thing. Why? Because this is a complex number. Okay, in signal processing, I will call this W, which has a very specific property. If I ask you to write this complex number in the complex domain, this guy, what is the length of this vector in the complex world? Is 1. All is changing is the phase. So all these bases that we're talking about are in fact on the unit circle. These are all the square, the roots of unity. Okay. And they are all multiple of one fundamental tone, which is the one which is defined here. If we define the Fourier as we've been doing so far, we will obtain the classic FT. If we define it in the way you were thinking about, we will have a different decomposition, but which has other good properties. Okay, is this clear? Another beautiful property of this is that it is symmetric. I mean, if I tell you what is the value of the basis number 10 at position number 20, or the other way around, is the same. So this is exactly the reason what is behind the FFT algorithms. When it comes to taking the multiplications, it uses this symmetry to be much faster in the multiplication, okay? Is this clear? Okay, should I tell you something else? The minus. So the way we define the transform, was the inner product of your, so let's say the Fourier, the component K will be the inner product of my signal with respect to a basis. Let me call it M. So this would be Kn. Okay, and it is in the inner product with the complex term that you will have the conjugation coming, and the conjugation will bring you the minus. Okay, but the basis is this: the inner product will make the minus come. Okay. So the minus. Yes, exactly. So now I want you, and I think I've done it, and I think you have already the solution, to build the Fourier matrix from that. Is it already there? Good. Then put it. There's one small trick. And it depends on the normalization. In Python does it one way, everybody does it in various ways. I think here, what I was doing, I was adding square root of n, okay, to make it orthonormal. It's just a normalization. I think Python doesn't have it, huh? The square root of n. I added it. It should be here. When you take f of t, it's not normalizing by the square root of n. No. For me, I defined it in this way. So I defined the W as x of j2 and pi over nx. Okay. I initialize the matrix to be something square and of type complex. And then I just loop over I and j, taking all the powers. This is a van der Waals matrix. Who mentioned the van der Waals matrix before? This is really the essence of the van der Waals. You see, do you follow how what is happening here? This is a very bad way of writing, of preparing the Fourier matrix. I will then ask you to think about a much better one. We will discuss this. And then you have the check. Do you have this in your code? Did I give you?
I have this, but not the phi f I j.
Ah, okay. Good. Because this was where I was asking you to compare our implementation with FFT. But before we do that, okay, you have the solution here. But I would like you to tell me how this framework changes for Fourier. Okay, so this is our encoder or transform. And now let's say that I replace B with phi, let me call it phi f. You will see in the course I will put a small letter below to say this is Fourier, this is POD, this is UND, and so on and so forth. So first of all, what will happen to this? Say then it will go. And this is, in fact, is a DAG, but our Fourier matrix has this special property. So I don't need to DAG, I just conjugate, exactly. So my Fourier transform is going to be equal to Fourier conjugated times U. Okay. And now I come back. Well, I will come back in this way and will just be, so sorry, conjugate, this is conjugate, okay? I come back, it's just this. This is the moment where I ask the machine, okay, what is the, you see that going back and forth is just a conjugation. What happens? I ask you the question, you think it over tonight, and you revise tomorrow. Okay. What happens if I take the Fourier of something 4 times? So I take my signal, Fourier transform. Then the result, Fourier transform again. The result, Fourier transform again. The result, Fourier transform again. Taking the Fourier transform 4 times. What do you think is going to happen? As I said, you think it over and you tell me tomorrow. But you noted that. Okay. May I in charge one of you to remind me tomorrow about the question?
I will.
You will. So Fourier times 4 times, what happens? Okay. But anyway, we saw that it is incredibly easy to go back and forth. And here you should check the check and gives you identity. You should check that the Fourier that you get is the same on you doing this or doing FFT. This NPL close is a way to check the 2 vectors are exactly the same. So you should be able to run this and plot the result. And now I have to go for the break.
We break now again.
5 minutes. Okay.
Okay, guys, you want to grab something? Juice, coffee?
Right.
I think it all
Stay the same.
Yes. You're right. Okay. Okay, guys, so welcome back. Now we do a final sprint. You can close your Python file. Now we go paper and pen. And we will leave the exercises for this, or I will leave it for you to play whenever you have time, maybe tomorrow morning or whatever. And we will take Python again tomorrow. Okay, so now let's follow me with the math. And I will also try to condense much more than what is in the slides because of the time. Okay? But let's recap a bit of what we have seen with this exercise. We have seen already the notion of encoder, decoder, and autoencoder. Okay. And now with this third lecture, what I wanted to give was somehow the dynamical system perspective of this operation. What do I mean by dynamical system perspective? I mean that now the data sets that we are going to consider are evolving according to some dynamics. Okay. And here I wanted first to make the link with this idea of autoencoders, which in machine learning is usually done using nonlinear transforms. So for the moment, we have been playing only with linear transforms. Okay? What you see here is the only linear way of doing that. Well, with B being any arbitrary basis. But we could add the nonlinear functions in between using the neural networks, if you're heard a bit about that, and make this much more fancy with the same philosophy of somehow having a vector which is of dimensionality, say D. I want to compress it. That's what we already did today. And then I want to be able to recover it, an approximation of it. Okay. Now, as I said, this is more or less what we've been doing so far. So you recognize these equations, and then in the slides, I'm making a parallelism between what is called supervised learning and unsupervised learning. So we look at the same equations that we have derived so far, but you can look at them through two different perspectives. In supervised learning, usually, which is what we did with the polynomial regression, we wanted to learn a mapping from an x, that case was from -5 to 5, to a y, which in that case happens to be the sines of 5. But it's a mapping from one word to another word. And usually, in this case, we have an analytic expression for this basis. So we gave the Legendre, the Fourier, etc., etc. Okay. So this is somehow built in the way of having a regression, which is supervised learning task, finding a mapping from an input to an output. This is why it was called linear regression, because the problem is linear with respect to the weights, which are the ones that we have to find using this formula which you see. Nobody in the linear regression will talk about encoding and decoding. Okay? They will do that more in dimensionality reduction. What is the difference? The math is the same, everything is the same. The only difference is that now you don't want to learn a mapping from x to y. You are just handling x. So I'm just giving you a vector and you want to compress it. That's it. You're not using that vector to map it into another vector. Doesn't mean that after you've done that, you cannot look for a map. Yeah, that was the question of Jacques before. But we will only stop at the problem of representation. I'll give you a vector, you find a compressed way of representing it. And usually in this case, we will not have an analytic representation for this basis matrix. In the folder, I gave you my favorite tutorial on this, which is using a special kind of autoencoder, which is the PCA. And in this tutorial, I know for me, you find the link here, you're building a classifier, phase classifier. So the data set is the data set which has all the employees of the Olivetti company. And you want to build a classifier that says, okay, this is person 1, this is person 2, person 3, and so on and so forth. So in that specific case, every vector, the one that we want to compress, is an image. In this case, because for illustration purposes, this image is very, very coarse. So it's of 64 times 64 pixels, which is still a vector in a 4096 dimensional space. Okay. Imagine that you have this space, you reshape it, and you encode it. What does it mean to encode it? It means write your face as a linear combination of a basis, basis phase. In the literature, these are called eigenphases, and we will show soon that this comes from the PCA. In fact, you will see this tomorrow. But the philosophy, when you look at the philosophy, is that you're representing every image as a linear combination of a basis of images, okay? Which are this one. They look like ghosts, but essentially the idea is that all phases can be written as a linear combination of these ghosts, okay? What happens in this exercise is that you can show that an approximation with 150 ghosts is quite good. Means that I need 150 modes or ghosts to represent something which lives in 4096 dimensional domain. Remember the cartoon of the cat or the dog that we were seeing before, okay? So if then the problem goes from this dimensionality to this dimensionality, a classifier can work much more easily here than here. You see also one more application of the idea of compressing it. It's all based on these formulas. In the same way I ask you to give me the special case for Fourier in this framework, I can ask you to give me the PCA for this framework, because the PCA will just change its own V. Okay? All linear decomposition will have their own V. Once you have your own V, you have this framework, you can do whatever you want. Okay? Do you have a question on this?
Isn't PCA the same as PCA?
Good question. ZNI. I will come back to that. So is the PCA the same as POD? And the answer is, in the framework with which we will play, the answer will be exactly yes. But let's put it like that, the POD can be generalized to other inner products where the PCA is a more restrictive case. Okay, it's usually the PCA is the POD where the inner product is this one. Okay. But the POD is a more general concept. I will build it also with other inner products than that. For instance, weighted products, or I can build the continuous with the integral and so on and so forth. Okay. So I could argue the PCA is a special case of POD. Okay. Everything clear? Now, I will not ask you to do this exercise. I leave it to you. Given this encoder, what happens if P is orthonormal? What happens if P is square and invertible? What happens if P is square and orthogonal? You feel this, okay? I ask you to feel this one. Normally, by time we will do this together, but I ask you to do it, okay? And Sarah will remind me tomorrow to check that you've done it correctly, okay? Now I want to go into the dynamical perspective. And when I say dynamical perspective, I mean that the data which are showing, unlike the phases of the Olivetti data set, are following a certain dynamics. It means that what happens at time step 10 somehow depends on what happens at time step 9 and time step 8 and so on and so forth. So there is a dynamic which I featured as a sort of dynamical system. And this dynamical system is producing many snapshots. Okay, I will assume again because of my bias into dynamics that the columns of this big matrix contains a snapshot. Okay, so the dependency on space, and I sample each of them after the other, and I have time. What's the dimensionality of this matrix? So let's write it because we will use it. So D for me will be of size NS times NT. So number of points in space times number of points in time. And now you can imagine what's coming next. In fact, let's assume that I apply the formulas which we have seen, so the encoder, on each of the columns of this matrix. So in the same way we converted before when we were here. In the exercise, we had the sinusoidal was 300 points, and you approximated with 4 numbers, of which 2, by the way, were 0. Okay, so de facto you approximated with 2 numbers. Okay, so you build an encoded representation of that view. I gave you 300 points. Let's take that as an example. This was 300. This was 300. I say times 4, but in fact it's times 2. This was time 1, so 4, and here you have 4, blah, blah, blah. Okay, this was 300. This was dimension 4. Imagine that now you do this to all the snapshots of the sequence. So to time step 1, time step 2, time step 3, all the way until the end. Okay. What you would do is basically repeat the same operation on all the columns. And to repeat the same operation on all the columns, all you have to do is to apply your linear autoencoder on the left. Okay. The result of this will be a Z, which will basically be of sides. In that exercise will be 4 times NT, because each of those n of those snapshots has been compressed to 4. Okay. You will now argue, yes, but I will do the encoding also along the rows and not along the columns. Yes, but we will come back to that. Okay. Let's start first thinking about the encoding only along the columns. Do you have questions? Everything is clear. Now, if you write it in this way, this will be the way people in machine learning will write it. And this will be called, for instance, what you will use when you do the PCA. Okay. We generally don't like, for instance, this would be a typical PCA. If you run a PCA where these guys are a specific basis, which we'll see tomorrow, then this will be the PCA score. So each vector here is so theta 1 is the reduced representation of P1, theta 3 is the reduced representation of P3, and so on and so forth. Okay. In model analysis, we don't like to picture this in this way. We rather picture it in the transposed fashion. In POD, you will picture it in this way. In PCA, you will picture it in this way. What does it mean? When I look at the first row, I am basically looking at the evolution of the first coefficient. So let's assume that before I gave you sinus of pi, right? And this was mapped to 4 coefficients, which were, I don't know, 1, 0, 0, 1, 0, or something like that, let's say. This is your z associated to that. And this is a vector. Now assume that time passes, I have another snapshot, another snapshot, another snapshot. If I do this encoding for each of them, then maybe the second snapshot will have 1.2, 0.2, I don't know, 0.3. This will be zeta 1, this will be zeta 2. And then if I do it for the third, I will have no other numbers here. What does it mean to look at the raw picture? It means that when I look at A1, I want to see how the first term of my basis has been changing through the time steps. Okay. So in the previous case, we had our basis was 1 x squared x cubed. I'm going to ask you, how is x evolving through all the snapshots? Is this clear? The difference is very subtle, but if you want to use an algorithm to do PCA to do PQD, you can. But just think about the fact that usually the shapes are shifted. And moreover, we saw you can picture it in this way. Okay. And the last ingredient to complete our model decomposition is that we usually, I don't know where you are here, but we usually don't like to have this vector to have any length. We will normalize each of these vectors, okay, so that they have unitary length. Assuming that these already have unitary length, because I've chosen them to have unitary length. Now I also pick this one to have unitary length, so I'm normalizing it. The normalization of this is usually written in this way. And the annual marker contains the length of this A1, A2, and so on and so forth. And then here you have just the normalized version of our rows. If you plug all of this back together, you arrive at the fundamental decomposition. You see it? Do you have questions on that? It's quite clear. So what we are doing is we are writing B, which is a matrix, as a linear combination of matrices. So let's see. If I ask you now to look at that. So D is sum of sigma pi times psi transpose. Now phi is a basis for the columns of D. So what is the dimension? NS. So this is NS times 1. C is the basis for the rows of D. So the dimension NT times 1. If I transpose, this is 1 times NT. So this is an outer product. The size of this is NS times NT. So this represents, if you want, the dynamic of the first of one model, of one terms of the distance, how it is evolving in time. Okay? And this tells us how that dynamic is important. So this is would be a scalar for us. Okay? Is everything clear? There is only one last thing before I close the puzzle. But first, I show you in practice how you have to picture that. Because now you should complain and say, well, but my matrix B, I put vectors in this in each snapshot. What if I have a floating? Or what if I have a video or something that is dimensionally much more complex than just a vector? All the operations that we are dealing are completely invariant to the shape that that you are giving to this vector. So let me take an example. Let's assume I have a velocity field like the jet, which you will analyze tomorrow. Is that as any point on y and any point on x and any point on y, and there's also two components because it's a velocity field u and v. Well, you don't care about this shape. You will just, for instance, take all the columns of this matrix, lighted, pull it one below the other. You do this for the u component and the v component. You pile it up also one below the other. The message is that every snapshot is whatever you had at time step k. Okay. If this is a 3D, a complex thing, you just reshape it as a column vector. Okay, and you stack together all the column vectors. So this will be the way I noted it in the slides. When I write dk as a function of I, I'm saying the snapshot, the kth snapshot. The I index here depends on how you have reshaped your matrix. If you have reshaped it by row or by columns, you will read this number in a different way. But at the end of the day, take as this index as a way to scan through all your data. If I write it in this way, then I'm looking at one time series. So every snapshot is a flow field, and every row is a time series at that specific point. Okay, this clear? And now we're back to this, to what we saw in the first lecture. Okay. So this will be now our factorization. The matrix which we put here, because of the way I have arranged, will be spatial basis. So if your data is a video of images, this will be images, will be ghosts. If your data is a set of velocity fields, this will be velocity fields, ghosts of the velocity fields. And every velocity field is a linear combination of these ghosts. This is a basis for all the time series that you have in your data. Every time series in every point is a linear combination of these guys. This way to picture it, if you have the space view or the time view. So if I look at the space view, I will picture this decomposition as a linear combination of spatial bases, the coefficients of which are changing in time. Okay. In this view, I picture every time series as a linear combination of temporal bases, the coefficients of which are changing in space. Okay, you see the symmetry? This will be a projection more, let's say, in this projection of spatial distribution on a temporal basis or a projection of time evolution on a spatial basis. Okay, you see the symmetry? The main bottom line for this, maybe you come back to that. Because this matrix is diagonal, you are not free to choose both this one and this one. Okay, is this clear? For me to develop a new decomposition, I don't need to invent a new phi and a new psi. I only need to invent one of them because the other is automatically coming from that through a normalization. Okay, so all the decomposition we will see tomorrow. Tomorrow we will see POD, DLD, MPOD, spectral PODs. They all, I will sell them to you as variants of different phi's, and then you can project to different D. Okay. So that now we go to the Fourier. Then we will close. We have seen already a very beautiful the Fourier basis. Just beat it. We picture it as a basis in space. But as I said, as a more dynamical guy, I would prefer to picture the basis in time. Okay. So let's say that now you look at the Fourier basis as a temporal evolution. Okay, harmonic evolutions. We arrive at the DFT, which is the classic first order encoding. It's not data driven because you fixed the basis, right? You have picked a specific basis. And I would like to picture it in this way. Imagine that you have a flow field. This could be a video, or could be anything else, but it could be a flow field. Okay. So I have many snapshots. Each of these blocks represent the snapshots. And now let's say that these snapshots, if I sample it at one specific point, I have a time series. In case I have the two velocity points from P and V, I have two time series, the U and the V. When I pick one point, so I fix 1 times 1 time, I have two numbers. And so I have a velocity field. Okay, if I pick time step 10, I have a velocity field, I mean, the spatial distribution of these two points. But you can pick the FFT of this. Let's say, as you have just learned, you take the FFT of this and the FFT of this. Okay. Now you pick one frequency. How many numbers do you have? You have also two numbers. Okay. So for every time step here, you have a velocity field. For every frequency here, you have a velocity field. You agree? So the DFT will be what will happen when in the factorization which we have seen, we pick psi to be the Fourier one. And as I said, everything else comes automatically. So let's say that I want to write this decomposition. I don't need to put the transpose here, right? Because this is Fourier. So this you have, I gave you the matrix, the data, and this you have. You have decided that it's going to be a Fourier matrix, and you have already seen how to write it. What you don't have is this and this. Easy. Try to multiply by this. What is going to happen? We have D, this, and then we have this. Agree? Now this you have. You will say, yeah, I have the product of them, but I don't have each of them. But I told you that this is diagonal, and I want this to be orthonormal. So what does that look like? This will look like if I ask you to take the product of, say, Phi1, Phi2, Phi3 times sigma 1, sigma 2, sigma 3. What does this product give? Should give something like sigma 1, Phi1, sigma 2, Phi2, sigma 3, Phi3. Okay, this product gives us this. So if I want the sigmas and I have this whole vector, I just take the norm of this. The norm of this will give me, if I take the norm of this column, will give me just sigma 1. Okay, so normalizing each of them will automatically give me the sigma. And so I will have both this and that, and I've completed my decomposition. Is this clear? You have questions? It was fast, I know. But still follow about it? Okay. Now, this is the way the final result that comes. And in the next exercise, I am giving you some data set which we acquired in this paper. So this is time resolved particle image velocimetry of the flow past a cylinder. Okay. This is the setup. I don't know if you are an expert of mechanics. If you are, I can tell you much more about the setup. Otherwise, I just jump directly into the final result of the measurement, which seems to be more the case. So what is happening in this setup? So the rod was a 5mm rod. The wind tunnel is this big. So it's very small, but we are making the acquisition at 3 kilohertz. That's very rare for times of PAV to go this fast. Okay, it's quite fast as a measurement. And we have 13,500 snapshots. What is happening is this data set is the following. This is the animation, and basically we have the wind tunnel running at approximately 12 meters per second. This is the velocity in this point. And then after some time, to have the test case more funny, we reduce the velocity of the wind tunnel. Okay. Now you know from vortex shedding theory that the shedding usually occurs such that you have a precise frequency which depends on the velocity. But if you're changing the velocity, you will change the frequency. Okay. So since this data set has two steady state conditions, one where the velocity was 12 meters per second, and the other where the velocity was below, you will expect to see two different clear frequencies, one for the first shedding, the other for the second shedding. So this data set, you can get it by running exercise session 1 get data. So I recommend you tonight you just run this one. It takes a bit of time to download it. It will download the zip folder. It will then unpack a data set, which looks like that. There will be a folder where you have one that file that contains the mesh, so all the x and y points with the velocity state, and then many that file that contains 2 columns each with the U and the V. Okay, so this is the code that will produce this data set, and then you have a small portion of the code. So I put some auxiliary functions such as plot, field, text, cylinder, which will just make you a plot. You say which snapshot I want to see snapshot 8, 9. Okay. And you can also make animations. I put also a code, a script that will produce an animation from, say, snapshot 1 to snapshot 10,000 or whatever. And the exercise for you is to compute the DFT for this data set. Okay. Look at these guys and plot them with respect to the frequency. Okay. Is this clear? Then you have computed the files. Doing that, I hope you have followed this very well. If not, take a picture, because this is what we need. Okay. And from here you get the velocity fields that are associated to each of these modes. Do you want me to spoiler the results? No. So they are in the slides, in fact, but the way it is done in the code that I gave you is done through an algorithm that we have, a software that we have developed, but this is so easy that it will be very educational if you try to do it yourself first. So the first part of the code is just creating the snapshot matrix D. So this is just reading all the text files, reshaping them as columns, and then producing the snapshot matrix D. And then it says npz file where you have the data, and then you will load this data tomorrow many times because you decompose it into many different ways. This is the tool which we developed where we are putting all the decomposition. It's called Modulo. I did it together with 2 students of mine, and I put the folder of Modulo inside the folder that you have. So if you see the folder Modulo is because of that. There you have DFT, POD, SPOD, DMD, MPOD, many decompositions. Kernel POD, you have many decompositions there. Okay. One thing, don't install it like that, because otherwise you will install an old version which has some stuff that is not going to be compatible with the new data. So don't do this. You already have the folder, so you don't have to install anything. Okay. So if you run the file DFT, will in fact solve the exercise. I believe I gave you already the solution, but it would be nice if you first try it yourself. And the solution, well, here this is how you do it. This will be the solution that you have to expect. So this is the plot of the sigma versus the frequencies. You see 2 clear frequencies which are linked to the shedding into the 2 velocities. You see a very low frequency due to the fact that we have changed from a certain velocity to another velocity. If I plot it this is versus the frequencies, and this is versus their index. So from the largest to the smallest, you will see that they decay quite gently. Fourier usually converges very badly. Okay. And then these are the modes that you will see. So these are the first mode, most important one is linked to the mean flow. It was changing. Remember that the mean flow was going from here and then very low. So this will have very low frequency, of course. But Fourier can only picture this, as we discussed today, like that. Okay. So the Fourier approximation of the first mode is this. Okay, because of what we saw before. And so that best correlates with this mode is this. Okay, it's the mean flow. Then the second mode will be the best flow field that correlates with a certain frequency, which guess what is one of the shedding frequencies. And so we'll pick a vortex shedding at a certain frequency. And the other one will be the one that best correlates with this one, say, which is at a much higher frequency. Usually, since in Fourier you have written what should the temporal basis be, we'll not ask Modulo to plot it because it's just plotting the anharmonic, which you already know. I think the exercise then closes with yes.
Let's say before feeding the data into DFT, we subtract the mean field velocity from all the snapshots, do we see at the plot the frequency versus the previous plot? We don't see a maximum at 0.
Very good point. Very good point. Thank you very much. In fact, I was not entirely correct when I said that in Fourier, the first mode is this. The first mode depends if the first is in terms of Python or MATLAB. Okay, the mode number 1, I mean, the first column of the Fourier, you remember what was the Fourier basis? Was this. So when I pick an entry, say here, when this is the index 0, or this, when this is the index 0, either of these guys is 0. So what happens e to the 0 is 1. So the Fourier method will in fact have a vector of 1 normalized by square root of n as the first basis, which is the mean. Okay. The second one will be the one associated to what we were discussing before. Okay. So I was asking, if I remove the mean before doing the DFT, what will simply happen is that at the moment in which you will compare your data with the mean, the answer will be 0. Okay. So in the spectra that you've seen there, what you will have is that the entry that corresponds to frequency 0 will be exactly 0, a sharp 0, because you have removed the mean. But the other modes will not care about that. They will be exactly the same, which is not the same as in the POD, for instance, or in the other decomposition. For the DFT, what will happen here? Nothing, but this first guy will be set to 0. Okay. For this specific test case, which is not in stationary condition, you will still observe the first mode being something like that. Okay, because I mean, if your mean field is doing something like that, what is the mean of this? I don't know, something like this, but it will still give you a mean flow. Okay, is it clear? More questions? No? Then the last part of the exercise is to build, here you have all the codes, you will build an approximation. And I tell you, pick the first 50 DFT modes, which will be an encoding of the dimensionality 50. So we're using 50 Fourier modes. And this is the approximation that you get of the velocity. You get quite a good approximation. You are blurring a bit some details, of course, when you have modes. And what we are basically doing is this. Okay, as we reduce the number of modes, we are distilling it and distilling it and distilling it towards its most essential thing. But still, if I were to transfer data, I have now to transfer you a matrix B, which was of size, I think this was 13,200, and this is like 4,000. But if I encode it in this way, I only need to give you 50. Okay, 50 modes, and then the sigmas. You reconstruct it on your side. Okay, so I will have to give you to make this approximation. You will need the 50 columns of this, 50 numbers that corresponds to this. You don't need to give me Fourier because I can rebuild the Fourier on my hand. So you will have to give me a total of 50 fields and 50 numbers. It's a good compression. Questions? Well, it was fast, but I think it covered the whole philosophy. The slides go at a slower pace, but if you go through the codes, you run it, all of it will be, yes.
How do we know how many modes they?
Very good question. You generally don't. There are various criteria. There is no, it depends a lot on the application. There is no golden rule to say which one to pick. Usually you might say, pick a such that I have 99% of the energy, or pick such that the slope of this has reached a certain conservation. There are many criteria, but to me, it's very much test case dependent. There's no a general rule that you say I will always do it in this way. The two most common criteria are, if you look at the sigmas, one is to say, okay, I will pick until the last one that has 1% of the first one criteria. Another criteria would be, no, I want to look at the slope of this. I will stop when the slope of this starts to flatten. It means that you are not adding so much more information when you add more modes. Okay, this is called screw plot. This is one energy based. You have values. More questions? Yes.
Close because the signals.
Yes. Yes.
The product.
So you start from here, you multiply, write it down, maybe it's easier. You multiply by psi conjugate, which you also know that can be done in a much faster way by just taking the FFT by rows. Okay. So let's do a concrete example so that maybe you are 100% sure. Let's say that your data matrix D is of size 1000 times 100. I have every vector is of dimension 1000 and I have 100 of that. My Fourier matrix is going to be of size it's a basis on time or on space? It's a basis on time. Good, very good. This will generally be 100 by 100, and this would be 1000 by 100. Okay. Now I multiply with that, so the result of this is still, so this operation here is 1000 times 100. So I have all the modes with their amplitude. I make a loop, I go column by column, and I look at the norm of each column. Okay, because I know that this has to be a diagonal. Okay. So when I look at the norm of each column, I will find all the sigma 1, sigma 2, sigma 3, sigma 4, and at the same time I have the phi. So in the code you will have a loop like that for n in range 100 in this case. What you will do is you pick, you have defined, you take sigma to be like that. I do sigma n. So sigma is a vector. I don't need to store it as a matrix because it's just a vector, right? Otherwise, if you want to do this, okay. And then this is np dot lin alg dot norm of what? Of the result of that. Usually I have called this sigma psi. I take all the column, so like that. This would be my sigma, and then my psi will be that thing divided by a scalar, in fact. Okay, where this one is the outcome. So the matrix of phi sigma, if you want, is either the outcome of doing d dot times say F transpose, or just take the FFT along the rows. Okay. Because of this normalization, you understand that once you have moved this guy on the other side, the rest is a normalization. Okay. And the way it was so simple to move this guy on the other side because this is Fourier. If this basis was something more esoteric that you have invented, you can still move it on the other side using the full big guy here, but acting on the other side. Sorry? No, I didn't say. Yes, it would generally be harder, but you can potentially do that. So in this case, everything is single because this is orthonormal. Want to know an example of a decomposition that does not have orthonormal temporal basis? the DMD. Okay, which we'll see tomorrow. I think we can close it here. We got it today, and see you tomorrow. Okay.